All right. Welcome back, everyone. Sorry for all right, welcome back, everyone. Sorry, we had AV problems. We reset the system, but it doesn't work either. So I just had to hello guys. Sorry. So a little bit delay. My apologies. For some reason this computer decided not to work. All right, so if you remember last time we were talking about memory safety. We started with like talking about what is the problem of memory safety, and then we talked about let me actually just make this full screen. Okay. And then we don't need this. Okay. Perfect. All right. So last time we were talking about memory safety attacks. We started talking about buffer overflow, and then we move on to code reuse attacks. We talk about various different types of code reuse attacks, and then we start talking about how we can protect the systems against these type of attacks, right? We introduced the notion of stack canaries and then ASLR and X plus W or DEP. And then we talked a little bit about control flow integrity, and we said that we're going to actually come back to this during this lecture. Then the last thing that we were talking about, and we kind of didn't have to finish it, was instead of trying to kind of prevent it, maybe a good idea would be to try to kind of search for these errors and remove them from the source so that we don't have even any. Hopefully, we don't have any vulnerabilities like memory safety vulnerabilities. And this goes under the category of kind of binary analysis or source code analysis that we're going to talk about a little bit now. So generally, there are kind of two things that you can do in order to try to find this memory vulnerability. So for example, you can say that, okay, there are some specific functions that I'm worried about, right? There are particular functions that doesn't check the bounds or functions that reads inputs but are not memory safe and so on and so forth, and trying to find those patterns, right? You can also like define different rules and trying to find those finds scenarios where those rules um, are not followed. And this generally goes under the category of software testing. So same ideas basically applies to generally any software testing. Doesn't necessarily need to be memory vulnerabilities, but particularly in the security context, what we are really looking for is particular memory safety issues. For example, we can say, okay, if there are unbounded writes, print a message or change it and so on and so forth. The biggest challenge with static tools is scalability because you have no idea which path in your program is going to go. And then for programs that has millions and millions of paths, this means that in order to kind of go through the control flow graph and finding all these patterns would be a humongous challenge, right? So especially, we have things such as loops and so on. So this could be a very, very challenging problem. There are tons of tools for this. So probably some of you have played with these tools, like IDA is the most famous one, Anger, Clee. There are various different things that can happen if you have the binary and you don't have access to the source code. Typically, starts with disassembling the code and looking at it at the assembly level. Most of these tools try to look at it at more higher level. So typically this is a process we call lifting. So you kind of like go from assembly level to a little bit higher. Higher means that closer to like, English language, the way that you can understand things. Many of these systems work at what we call IR or intermediate representation layer. For example, CLI is kind of like that. This is usually helpful with like if you have the access to the source code and then you can go to the IR layer. Uh, Most of these aesthetic tools is basically trying to analyze the control flow or data flow. Remember that we had data attacks and control flow attacks. So they typically kind of like, do these things and then go for, finding the patterns, as I said, check functions, understand the execution, trying to find for known bugs and all that. So essentially, once you have access to the control flow graph, so like, start with the binary, you kind of disassemble it and get the assembly. If you have more information, for example, if you also have knowledge of source code, you can also go to the intermediate representation, and then using this, then you can start like scanning like usually you start with like, drawing the CFG and DFG. Sorry. CFG control flow graph and data flow graph. And then you kind of like then based on that, you kind of do various different analysis. Later on, when we were talking about CFIs, you will see that why this is also very important for CFI analysis. Um, so that's kind of static tools. The main challenge with static tool, as I said, is the coverage issues. Because in CFGs, when you're looking at it statically, essentially all of these paths are possible, right? So, for example, this one can go into, many different paths here, and then this can go like quickly. This gets really out of control, right? So it can go like really, really deep into the tree because there will be many, many if then else's and then the function calls and then if then else's within function calls and so on and so forth. Especially think about, for example, trying to do a static analysis for Linux kernel or like a very, very sophisticated program, very complicated program. These things would be very hard to analyze statically. So there's usually there's kind of like, finding like every single instruction, every single path is an issue. So typically the static analysis tools like have some notion of approximation. So say like you have this usually is with the coverage. So out of all the nodes that I have in my CFG, how many of them have I visited? That gives you a little bit about what is the coverage of this system. So that's kind of like, the main kind of the challenge in static tools. To kind of fix this issue of the coverage issue of static tools, there are lots of dynamic tools, okay? The idea of the dynamic tools is that, okay, instead of like going through every single path in the program, let's actually run it with a bunch of inputs and see what exactly is the path that's being taken, okay? But this immediately reduces the search space to all the possible paths to only path that's been taken, okay? Of course, there is like a big challenge, and that is how do you even run this? Especially keep in mind that you're trying to do security analysis. It means that this code is potentially a malicious code, could be a malware that can destroy and negatively impact your system. So running this has to be very cautiously, executed. So there should be usually isolated environments, sandbox environments, and so on and so forth. Uh, there are various different tools for dynamic analysis. This is one of the famous one is pin tools. So for example, there is like a code like this. This is assembly code for Intel x86. You have a move and then you have a compare and you have a jump. Uh, the way that pin tools works is that it's basically they call instrument the code. So you can try to add additional debug information here such that this information can be spitted out once you run this. So for example, what you can do is transferring that code to something like this, that you can add your arbitrary code in between this instruction. So for example, let's say I want to know how many branches this program has. There are actually APIs for pin tool that you can add here. And whenever you have a branch, then you can kind of collect that information. Think about it as like a counter that you can add to your C-level, high-level programming languages. The nice thing about this is that as you run this on the real hardware, it will collect that information and spit it out to you. So you can, once you run that program, then you can see, for example, this program has this many branches. this many of them has been taken, this many of them has been not taken, and so on and so forth. The nice thing about this is that you can quickly then follow the CFG, right? Because essentially what you can do is that at the beginning of every basic block, you can have an instrumentation that basically collects the basic block ID, right? So you can do that. You can also do the data flow. For example, every time that some number has been written, some address has been written, you collect that information. Essentially, pin tools and tools like pin tools give you lots and lots of flexibility in terms of what you can collect during the runtime. Okay. Of course, this means that your runtime is impacted. So generally, these instrumentation tools are invasive, and they have this thing called observer effect, which means that essentially what you're running no longer is the original code. It's the original code plus the things that you're adding. So this might negatively impact the system and could have like this observer effect. But if your design is not negatively impacted by the observer effect, you can collect this information. And this is very, very handy tool for many systems. Again, doesn't necessarily need to be for security research. There are many people using this, for example, for finding performance bottlenecks. For example, if you see that your code has lots of cache misses. So for example, here I can basically collect cache misses. So if there is a cache miss, for example, I can plus some value, okay? So, and then I can see that, oh, there is a function in my code that there are lots of cache misses happening in that code. I can probably change the, data patterns and the way they access memory to make that better, right? So the same idea applies for memory safeties, right? So I can check, again, I can create different set of rules and try to find that. I can at least, create my CFG dynamic control flow graph very easily using this tools. Okay. If you haven't played with like Intel pin tools, I definitely recommend to take a look at it. There's other tools like Valgrind and so on and so forth that you can also do. There's also many of operating systems called with what we call performance counters. So for example, for pin tool, you need to actually recompile the code with your own APIs. So that has like an additional steps that requires. But performance counters are generally these additional. So for example, if you have a system with a CPU, typically these CPUs have some specific registers that basically count things as you're running them. So for example, number of branches, number of cache misses, and all that. You don't need to even tell the processor to save that. It's just naturally hardwired into the system. And there are APIs that are usually accessible through the operating system that you can actually read this performance counter. So there are tools in the Linux, for example, that you can actually access this performance counter. So the famous one is called perf. Of course, you need to have privilege, usually root privilege to read perf. But if you, for example, look into the perf and the documentation of perf, you will see that there's like tens and tens of different performance counters that you can read through perf. So you can run your program, you can read perf values and see, for example, how many different instruction has been run, the instruction mix and all that. Again, very useful tool for not just security analysis, but generally software testing and performance analysis as well. That's why it's actually called perf. Yeah, so this is kind of like the story of dynamic analysis. Of course, there are other tools as well, like Anger, for example, is like a very famous one. QEMU, Quick Emulator, is another famous one. Quick Emulator is actually try to emulate the hardware. So it's try to, instead of actually running it on the real hardware, you run it on a piece of software that mimics the behavior of the hardware. The nice thing about this is that then you're not like limited by the observability problems that you have in the hardware. You essentially reading any values as simple as adding another function to QEMU. So QEMU is actually very, very sophisticated software tools for all of these analysis. The problem with QEMU, although, is that since it's emulation, it's not as accurate as hardware simulation, running it in real hardware. But this is the process that we typically call rehosting. So you're kind of, instead of running it on real hardware, to run it on an emulation. Yeah.
For QEMU, is it like treating it as an actual hardware model, or is it kind of just like abstract like syscalls?
So it's an emulation, so it doesn't go through like the cycle accurate simulation, but it's can get as close as you want. So it's mostly trying to just at the ISL level try to emulate the system. So it can understand the difference between, let's say, an add instruction versus a move instruction versus a subtract instruction. But it doesn't understand, let's say, whether this is a cache miss or branch miss prediction and stuff like that. Although there are, for example, plugins for QEMU that adds cache to it as well and other things, but it doesn't go through that. Usually, if you want to get more information, you go through the simulation. And then there are tools that simulate the underlying hardware, like Gem5, for example, right? So Gem5 is also, you can run your software, you can run it through Gem5, and it gives you not only kind of like the mix of instructions and branches and all that that you can get from QEMU, but you also get things such as, oh, what is your cache behavior and what is your branch predictor behavior and all that. But again, both of these are simulation, which means that there will be a semantic gap between real hardware and these simulation tools. Okay. Um, but if you're interested, definitely like, Anger, for example, both QEMU and Anger are open source tools. There are nice tutorials for them. If you're interested to look into these, uh, uh, play with them. We used to have a project on them in the previous classes. This year, since we have less time, I'm gonna get rid of one of the projects so that you can work on your final project. So we're not gonna have a project on this. We're going to have a project on attestation that I'm going to talk about later in this lecture. But as I said, this is for your own interest, and you can work on these things and get a little bit more familiar with them. Okay. So both dynamic and static has the coverage issue. Dynamic is a little bit better because you can run it fast and you can run it on the real system. But still, since depending on which input, which path it's going to take, you're going to have similar coverage issues, okay? Because, for example, let's say your program has like, different path, uh, right? And these paths are based on the input. So for example, I don't know, like if x is less than 0, you're going to take this path. And then if x is greater than 0, you're going to take this path, right? So if your system is based on like the inputs that you're giving, and then if you're giving like inputs like this, then you're always going through this path and kind of to cover and explore the path on the left side. In order to go to the path on the right side, then you need like positive numbers, right? So depending on what sort of inputs you're giving, the path that you're going and covering in the control flow graph will differ. Why does it matter which path I'm going through? Because each of these basic blocks, there are a bunch of instruction in it, right? And your leaking instruction could be somewhere very deep into this graph, right? So for example, it could be somewhere here you have a memory unsafe instruction. So in order to find that memory unsafe instruction, you should be able to cover every possible path, right? But as I said, it's also a losing battle trying to find all the paths. So there is this kind of trade-off between how much can I explore versus how accurate my system is. And one way of kind of finding a good balance between them is this notion of what we call fuzzing. So the idea of the fuzzing is I create some inputs. Let's say I start with random set of inputs. Let's say my program takes two inputs, X and Y. And based on X and Y, it can go into very, very different paths, right? I can start with, say, I create 1,000 random inputs and feed it to the system one by one. Let's say, for example, I have a dynamic Intel pin tool or QEMU or whatever I have, and I collect the outputs, okay? Now, how do I know how well am I exploring this path and different paths? I can do, I can create my CFG and I can kind of see how many nodes I have visited. So I will have some notion of coverage, right? But now the question is that if I want to run another 1,000 inputs, how should I create those 1,000 inputs, right? Should I just create another 1,000 random inputs, or should I do something better, right? And this is where this fuzzing come into the play. So fuzzing is essentially trying to help this coverage problem, trying to give you a more informed decisions about the type of input that you can create, okay? There are various types of fuzzing. Usually this is what we call coverage guided fuzzing. The idea of coverage guided fuzzing is that I'm trying to create inputs such that it gives me more explorations of different paths. Because as I said, the more paths I visit, the more chance I can find these vulnerable codes. Okay. How do I create this? I recommend you to go through the fuzzing algorithms, but to give you a basic idea is that how many of you are familiar with genetic algorithm? A few of you. So the idea of genetic algorithm is based like, kind of inspired by biology. The idea is that in order to create a new input, what I can do is that I have the previous input. I do two things. Either I kind of mix previous inputs together. Let's say, for example, I say I take half of this input and the half of this input, like lower half bits of the left input and the upper half bits of this, and this will create a new input, right? So this goes here and this goes here. So this can be one new input. Usually we call this offspring. This is how we also create our genes, right? So like, the parents create a child, just kind of like, combination of this. The second thing that we usually do is that we mutate, which means that we pick few bits of this offspring and we flip the bits. So for example, I said, okay, this bit and this bit, I want to also flip it. So if it's 0 becomes 1, if it's 1 becomes 0, okay? So this will be the new child, and this will be my new input. And I can follow this format. Usually there is also what we call a fitness function. The idea of fitness function is that, okay, this input that I create, I can create a bunch of these inputs using different algorithms. So for example, instead of like doing this left and right, maybe doing this and this, maybe the mutation that I do would be different. And then I have a bunch of different inputs. I feed all of these and see which one results in better coverage, for example, in this case. Fitness function could be anything, but let's say if this is a coverage guided problem, I want to have better coverage, right? So those that are creating better coverage, those that are visiting new nodes, I like those, right? So I go through that path. So I keep them, I get rid of the others. Then I create like, let's say these two created new path. So the next offspring that I'm gonna create will be based on these, right? So I'm gonna mutate that. Another thing that I can do is some form of a gradient-based kind of, ideas. So this becomes again an optimization problem. So I can again keep those that I like and get rid of the others, or kind of like make this in more optimization oriented problem. So there's tons of these optimizations for this fuzzing problem. Generally, the idea is that I want to create some randomness, but this randomness is guided and based on the knowledge that I've seen on previous samples. Does that make sense? The famous fuzzing is American Fuzzing Framework, AFL. It's, I think, created by Google. Take a look at that. It's also open source. There are lots of interesting tutorials for it as well. This is a little bit more. As I said, the goal is generate a sequence of inputs to test a program. Of course, you can start by just randomly creating, but the idea of fuzzing is that a good fuzzer is that something that creates you a better than random generation, right? So you start with some seed, you select some seed, you mutate those seeds, and then you put that input. You run it, okay? And you get some info, some feedback, right? So you're gonna see that, oh, this new inputs that you provided, that was the taken path, and you can compare that path with previous path, and you will see that, oh, this actually leads into newer path that I haven't seen before. So you get that information, feed it back to your seed, and then you create new new inputs. Okay, so this is like an iterative process. Typically, fuzzers runs for hours, few hours, days even, because you need millions and millions of inputs to generate in order to kind of go over the entire system. Good. All right, so now that we see that there is good things about static, because static you don't need to run it on real hardware, and then you can go through all the paths, you can create actually have some mental model of the entire CFG, versus the dynamic is more of like throwing rolling dices and see whether it works or not, because you can, for example, do fuzzing and always have only 10% coverage, right? So if your fuzzing kind of sucks, you never actually go and explore the entire system, versus static kind of guarantee that you can explore all the paths, but it's going to take a while for going through that. So this is kind of like the idea of hybrid systems, that maybe I can have a little bit of pre-analysis, static analysis, but in order to actually follow those paths, I can use a dynamic dynamic testing. So this is what we call symbolic execution. So the idea of symbolic execution is that instead of running things concretely, when you say, okay, input is equal to 2, I'll run this and it gets the values concretely, I'm going to assign symbolic values to my inputs. Let me actually show you an example. So let's say, for example, I have a code on the left, okay? So as you can see, the code on the left has this A, B, and do we have anything else? I think, yeah, Z, yeah, and C as my inputs. So depending on the value of A, B, and C, different things can happen here. My outputs are X, Y, and Z, okay? So for example, if A is equal to 0, sorry, A, for example, is equal to 1, then, for example, X would be -2. If A is not 0, is not 1, it's 0, then X would be not equal to -2, would be another value, okay? So here's what we're going to do. We're going to create our flow graph. So I'm going to create my flow graph, but instead of concretizing the inputs and my flow graph, I'm going to assign symbolic values to my input. So for A, I'm going to show it as alpha. For B, I'm going to show it as beta. And then for C, I'm going to show it as like lambda or gamma or something like that. And then what I'm going to do is that I'm going to create the symbolic graph of my design. So for example, I can start with like, so first line of the code is here. I'm going to say alpha. So alpha either could be true or false, right? If it's true, then I have X equal to -2. Then I'm going to go here. This is my beta. If beta is true, I'm going to go through this if then else, right? In this case, Z is definitely equal to 2. And then there is also another additional thing that, if it's not true, then I'm going to just go through this part here. Then again, I have beta not equal beta here, so this is false. So I'm going to go through this, and there is a condition on a not of alpha and C here, and then this could be true or this could be false. As you can see, depending on all the possibility of A, B, and C, I'm going to have different paths here, right? So how does this helpful? What would happen is that for all of these paths, I can create a formula. For example, I can say that, okay, in order to get to this path, what I need is alpha has to be true, beta has to be true, and I'm going to go through this path, right? So alpha and with beta less than 5. This will give me this condition for this path, okay? So how does this helpful? When I'm creating my inputs, I know that if an input that satisfies this condition will give me this path. The input that satisfies this condition will give me this path, and so on and so forth. So basically, this becomes what we call a SAT problem, which I have a big, equations of various different conditions, and I can go through the SAT problem and try to solve that SAT problem, which means that I'll create an alpha and a beta such that it satisfies this, Next time I create another alpha and another beta that satisfies this, and so on and so forth. So again, instead of just blindly creating random inputs, I can create specific inputs that hits exactly the thing that I want. Okay? So this is a combination of a dynamic versus static. So statically, I create this very complex equation of my symbolic analysis. Then during the dynamic phase, I find concrete values for my alpha and beta and so on and so forth to actually hit the particular path that I want to create. Make sense? Any questions? And again, why do I care? Because, for example, in this case, of course, there is no memory unsafe. But let's say like somewhere within this deep if then else, there was some memory unsafe condition. So if I have, as I said, set of rules, I can find that here. So it's important that I can go through that path. So then I can run my analysis of memory safety. Okay. How do we find that? How many of you know what is a SAT problem and SAT solvers? Okay. Interesting. Not many people know what is a SAT problem. Like, how many of you have taken any algorithm course in your undergrad, but you haven't seen SAT problem?
They taught at the end.
Okay. Which means,
This is the last 2 weeks of state of the Navy.
so you heard about it at least. Okay, yeah. So there are tons of SAT solvers. Z3, for example, is a very famous one by Microsoft. Again, these are open source problems. So a SAT problem is like this. Like, you have, let's say in this case, x1 and x1 to x3. You're trying to find a condition that makes this true. For example, like a true, false, true, or false, true, false. Make this condition equal to 1. We call this a solution for the SAT problem. Okay? SAT problem is an NP-hard problem as far as I remember, or maybe not. But generally finding this for a large equation is not an easy problem to solve. But yeah, you can, for example, formulate this, and this would be basically your symbolic execution. This would be your alpha, beta, and so on and so forth. You feed this to a SAT solver, and it gives you inputs, right? So it gives you true, false, true. For example, here is the assumption is that these are binary values, but this could be also, integer values or character values, and so on and so forth. But then once we have this inputs, then you feed that, and then you get your coverage that you like. Good. This is another example if you want to take a look, but I'll let you guys to take a look at it. I'm not gonna. So this is kind of like just showing you the difference between concrete and symbolic, right? So in concrete, you actually assign actual values. In symbolic, you assign variables, and then you try to solve those variables. Okay. So what are the challenges for symbolic? Symbolic kind of also have complexity with path explosion, significantly better. But creating those equations and creating those conditions is also not straightforward in many cases. For example, one big problem that symbolic execution has are loops, because loops create many different equations, many different conditions, but in fact, they're all part of the same basic block. So one thing that many people does is that doing loop unrolling or ignoring loops and all those things. There's also this thing called concolic execution, which is a combination of concrete and symbolic, which means that not all the input variables needs to be symbolic. I can concretize some of the inputs, and I can assign symbolic values and variables to some others. This way I have a combination of concrete execution and symbolic execution. That makes my equations term much simpler, so that my SAT solver can very quickly solve that. Okay, so this basically is what's called concolic execution. So you combination of concrete versus symbolic. Okay, any questions here? This general area of binary analysis and fuzzing is very active. Many people kind of like, looking at this space because it's, as I said, it's not just the problem of security, but also many software developers and software testers also deal with the same problem. So this area of concolic and symbolic and fuzzing is actually much more explored even in the software engineering domain. How many of you have seen this in your software engineering classes, actually? Okay, CPU of you. Good. Okay. All right, so that's it for memory safety. Basically, the module was trying to go over the potential challenges that we are facing when dealing with inputs in a system like an IoT systems. Unfortunately, the problem is that the codes are very complicated and unsafe. This unsafe language is here to stay, although there are lots of efforts in order to move away from these unsafe languages. But still, this is going to be a lingering problem for next few years or maybe a decade. Uh, so we learn about these different types of attacks, the control flow hijacking, and then we also learn a little bit about defenses. Unfortunately, this is kind of a vicious cycle that we have seen and going to continue seeing, that there is a vulnerability, fix the vulnerability, there will be a new vulnerability based on this fixed vulnerability, and then there's a fix for that fix, and so on and so forth. That's why this is kind of like a 20, 25 years of research when still we couldn't fully say that we have fixed this problem. Okay. Okay, so we talked about like buffer overflow, but there's a whole bunch of other problems in memory safety, like use after free, format string vulnerability, heap spraying, integer overflow, and so on and so forth. I'm sure many of you are familiar with these, but if you're not, there are general different types of these language unsafe actions that you might have, and it could happen in your system. Most of them will result in some form of a control flow hijacking or data integrity corruption. So lots of those defenses that we talked about exist in this. All of these binary analysis trying to find all of these. So for example, not only I'm worried about integer buffer overflow, I'm also worried about integer overflow. I'm also worried about use after free and so on and so forth. Okay. All right, so that's it for this module. Let's have a quick break, and then we're going to come back and talk about control flow integrity and attestation. All right, moving on. Oops. Okay. All right. So the status quo is memory safety is a critical challenge. There are different attacks ranging from simple buffer overflow to extremely sophisticated code reuse attacks. And there are several static and dynamic analysis tools and techniques, symbolic execution, static analysis, fuzzing, etc., etc. A whole bunch of runtime techniques also exist, like ASLR, stack canaries, depth, and so on and so forth. Despite all these things, there is memory safety is still an open issue. And there is also, for these solutions that we talked about, there are a whole bunch of runtime or storage overheads that we need to think about. So it's not necessarily say that, okay, there are systems that are still unsafe. There are systems that are indeed safe, but many of these safeties comes with huge performance or cost or storage overhead. So we need to be able to also balance it, especially when we are talking about IoT systems, more low-end resource constrained systems. We have to be very mindful of these additional overheads that we add to the system. There's also another problem because that caused this memory safety to be still an open issue, is that there are tons of these zero-day overhead, zero-day vulnerabilities. There are lots of these unknown problems that even if that, let's say we have a very sophisticated code analysis and binary analysis, we still couldn't find those because we don't know what we're looking for, right? So yes, I can find, for example, use after free, but maybe there are other things that I don't even know what they are. And in fact, well, unfortunately, history has shown that there are lots of those zero-day vulnerabilities in our systems. All right, So now that we know that, there is the secondary kind of second layer of defense in order to protect our systems against memory vulnerabilities and memory safety, and that is runtime monitoring. Okay, runtime monitoring can basically be divided into two things. Runtime monitoring can be for prevention. You can think about, for example, something like stack canaries as some form of a solution for runtime monitoring, but there is no notion of monitoring a stack canary. Well, there was because you check the values, but we're going to talk more about monitoring. There is a very sophisticated solution called control flow integrity. We're going to talk about that, and then there's also tag architectures, which is also goes under prevention. So these prevention solutions try to prevent control flow hijacking from happening. So there could be, for example, vulnerabilities in the system. The attacker can exploit those vulnerabilities, but what will happen is that the moment that try to subvert the control, these control flow integrities will prevent that from happening. Okay. There's also another class of defenses that tries to at least know whether or not something happens to the system, such that if, for example, this is a remote device, let's say there are two IoT devices talking to each other, receiving input from each other, if I can at least check the status of the other device and know whether or not this device can be trusted, I can at least, do something useful, because yes, I can not protect its security, but I can prevent it from infecting my system, right? So there are a whole bunch of works trying to basically detect whether or not a system is in the correct state or not. And that goes under the umbrella of attestation that we're going to talk about in this lecture as well. Okay. So let's talk about the prevention, the runtime monitoring for prevention first. As I said, there are two common solutions, very popular solutions. The first one is what's called CFI, or control flow integrity. The second one is memory tagging. I'm not going to talk much about memory tagging. There are a few papers, presentations next week that are going to go through a little bit of memory tagging, but I'm going to talk mostly about control flow. I'm also going to just scratch the surface for control flow integrity. Hopefully, again, there will be some papers next week on Monday. They're going to talk about both of these topics, okay? So generally, the idea of control flow hijacking is that, remember I told you that control flow hijacking was this scenario where, the address, the jump address, the branch address is overwritten by some adversarial address, right? So the adversary basically takes control of the PC, the program count. I gave you two examples. One was when you injecting your own code, right? And that was when the attacker not only kind of overwrites the PC, but also inject some code either through some offline phase or through the online phase and jump to that part of the program. We said that this is usually much harder these days. So what people do these days is using existing code. But in both cases, what will happen is that the adversary changes the PC to some value of their own liking, right? And they usually needs to continuously do that, especially for the code reuse attacks. So if I want this to be prevented, I basically needs to know whenever there is a transfer of the control, basically whenever I'm jumping, I need to know whether this jump is a correct jump, is a legitimate jump or not. That's the basic idea of a control flow integrity. Okay, that's why we say control flow integrity. Essentially, we are trying to say that, within the basic block, there's nothing I'm worried about. But after, from one basic block, I go to the next basic block, I need to know whether this transition, this transfer is a legitimate transfer or not. Okay, that's why I'm trying to protect the integrity of this transfer. How do we do that? Essentially, there are two things that I need to know. First is that there are two types of jumps and edges in my control flow graph. There are forward jumps. These are the jumps that I'm showing you here, that essentially you're from one basic block to go to another basic block. There's also some backward jumps or backward edges that you come back to previous basic blocks that you have already visited. Example of forward edges are like calls and indirect jumps. Example of backward edges are returns. Later, I'm going to explain why it matters whether this is a forward edge or a backward edge. Okay, so let's talk about the backward edge, and let's talk about how the CFI will work in a forward. Sorry, let's talk about forward edge first, and let's see how CFI will apply to forward. Essentially, the idea is uh, uh, this shouldn't be direct and indirect. Uh, So the basic idea is this, that I check all the transitions in the program, okay? This again goes back to the same problem that we just talked about, which is the coverage issue, okay? So CFI suffers from similar challenges that we observed in binary analysis and code analysis, because if I want to be able to observe all the branches, I need to go through every single basic block of the system. The good news for CFI is that I don't need to execute every single line in the program. I just need to be able to draw the CFG of the program and be able to see all the possible transitions. That's also not an easy thing to do, but it's much simpler problem than, let's say, figuring out whether my code has memory vulnerability. Okay? Uh, uh, so once I have that, I can list all the possibilities, okay? So I'm gonna have a very complicated basic block kind of CFG. But what I'm going to do is that I'm gonna, for example, assign numbers, okay? And then what I'm going to do is maybe I like have something like this as well. So I'm gonna have all the possible transition. So for example, I see that from 1, I can either go to 2 or 3. From 2, I can go to 4 or I don't know, like 5. From 4, I can go only to 5, and so on and so forth, right? Here, I'm just showing you like if then else's, but keep in mind that there could be also scenarios like this. For example, if you have an indirect jump or a function pointer, there is not just 2 possibilities. It could be many, many possibilities, right? So you can list all of these possibilities for these, okay? So you can record all of them. And then during the execution, during the actual runtime, what you will do is that you have this list. For example, let's say now in basic block number 2. And what I'm going to see is that the next jump will be from 2 to 4, okay? So now I'm going to go back to my list and see whether 2 or 2 to 4 has been something that we have observed before during our offline phase. Uh, if it is, then we consider this as a legitimate transfer, okay? Uh, if I haven't seen this and this is not a possibility, for example, I see that from 2, I go either to like 5, which is another basic block within my program, or maybe I jump to somewhere that I don't even know where that is, okay? So I don't even have a number for that. And this is kind of examples of those control flow hijacking that jump somewhere else in the program, right? So if I see kind of this transitions within my code that is not authorized, or transitions even outside the CFG that I'm expecting, these are the examples of a violation of the control, okay? So I can then quickly enforce and block this. How I'm going to block this, we're going to talk about it later. But generally, that's the basic idea of CFI. Any questions? Okay. So of course, there are questions about how do I find all the possible transitions? How do I enforce this? What is the overhead of this? These questions are great questions. Some of them you have already answered. For example, for the transitions, we were going to use similar techniques that we just spoke and told you about. For example, fuzzing is one of the very, very common ways of finding the transitions. Some form of a symbolic or concolic execution. How do we enforce it? The enforcement can usually happen either at the hardware level, so you can actually bake this into the processor, okay? So essentially, like whenever you have a PC, they're changing the PC, this is a register, right? So what you can do is that before writing this into this register, you kind of do some check with the like the all the possible checks. If this check is passed, then you write it to the PC. Otherwise, you raise an exception, you create an interrupt, you trap this into some unknown problem. So this would be like dividing by 0 or accessing a memory that you're not allowed to access, those kind of problems. So this would be within the same range. So I can implement this in hardware within my pipeline. I can also implement this in the OS, right? So OS can also do this. So I can implement it as a software layer into my system. So essentially every jump, I can instrument the code and I can check it using the kernel. I'm assuming that the kernel is trusted, but that would be much easier way to implement this because it's purely software. So there's no need to changing the entire CPU and hardware for it. Okay. So both of these methods has been extensively used. There are actually commercial solutions for both hardware and the operating system. And the overhead for this, there is a big overhead for the offline phase because I need to go through the entire program and store this. There's of course a runtime overhead associated with this because I need to check. That check takes some time. I also need to store and remember all the transitions. For a large program, this transitions, there could be many transitions. So I'm storing a lot of information. I need to access that information on the fly. And that's also additional problem that I need to solve for implementing this, okay? So let's talk about forward edges and backward edges a little bit more and see how the CFI works. So as I said, for forward edges, the idea of CFI is that, first of all, forward edges could be just regular jumps, could be function pointers, could be virtual calls. Essentially, if you have like a pointer like this, there could be, as I said, in many cases, could be just two. But in for the pointers and indirect jumps could be many different possibilities. The idea of CFI is essentially aesthetically calculate what are those possibilities, what are those kind of whitelisted or legitimate possibilities, and then save them. And during the execution, try to basically enforce them. So essentially, there are kind of two phases for CFI. The analysis phase and the enforcement phase. The analysis phase is computing the CFG and finding all the transitions. Enforcement is checking the observed transition and intervene if necessary. Okay. There are also lots of papers that tries to systemize this knowledge. For example, you can think about all the possible transitions that your control flow might have. You might have backward control flow. You might have forward control flow using direct jumps. You can have forward control flow using direct calls. You can have forward control flow using indirect jumps. You can have forward control flow using indirect jumps. And indirect jumps can be further broken down into function pointers. It could be exception handling, could be language features, and so on and so forth. These are dependent on the language and the operating system that you're using. But generally, CFI can be further broken down into all of these little details, and you can apply various different technologies and techniques in order to achieve all of that. But everything except this first one, which is a backward, okay? So for the backward, we're going to have something else that we're going to talk about. But for all the forward control flows, CFI works really well, okay? But again, you have to be mindful of these different ones. Why? Because, for example, a function call could be various different function call, but it's a finite number. But something like the indirect jumps could essentially take any number, right? So you're gonna have lots of problems for like indirect jumps because technically indirect jump can jump to anywhere in the program. And unfortunately, many of these CFIs are attacked because of those indirect jumps. So there are like additional measures that you need to implement to protect against indirect jump. I think one of the papers next week gonna talk about that. If I remember correctly, but if not, you can always go and check out existing solutions. I talked about how to implement this. Could be hardware, software, or operating system. There will be performance implications. Lots of these solutions are not talking necessarily about security, but they are trying to improve the performance of this because I need to check these during the runtime, which means that I need to stop the execution of the actual program and do these checks. So I need to be able to do these checks as fast as possible, right? So I need to be worried about those. A very good resource for this is this survey paper called Control Flow Integrity, Precision, Security, and Performance. If you're interested to know more about CFIs, I definitely recommend you to take a look at this. As I said, on Monday, we're going to also have paper presentations mainly on CFI. So you're going to see various different concrete examples of CFI. Okay, questions? Good. So what about backward edges? Why do you think CFI does not work for backward edges? Too many possibilities, right? Because essentially backward edges are mostly return instructions. And if you remember, I told you that you can return from, we can return to any point in the program, right? So there is no specific points that you can return. You can return from any point. You can return to any point in the program. Whenever you call the function, you will return to it, okay? So that's why backward edges, of course you can have CFI style for backward edges, but then essentially that means that you have to remember every call site, right? Like you have to add this for every single place that you create, you make a call. And then again, this quickly gets too large for real programs that has many function calls and many return calls, okay? Versus, for example, in the number of jumps and indirect jumps are usually finite number. You can quickly go through the statically go through the program and find that. Versus a function call could be within a loop, and every time that you call a function, you need to do something like this, which is a challenging problem. So how do we fix that? There are various solutions. For example, there are tag architectures that tries to kind of like assign a tag. There are other form of architectures for this, but the popular solutions for backward edges are what we call a shadow stack. Okay, so the idea of shadow stack is that, remember we talked about stacks and how we put the return address into the stack. So we push it into the stack, and that's how we remember the return address. The big problem with normal stack was that normal stack was vulnerable to buffer overflow attacks. Well, what we can do is that we can have another stack, which is the copy of the normal stack, and we call that shadow stack. The good thing about shadow stack is that I can use the shadow stack only for storing the return addresses, okay? So I'm going to separate my regular stack with my shadow stack, where shadow stack would be either just a mirror of my regular stack, but not writable by the programs, or I can just use it for storing my return addresses, okay? The way this works would be this. So let me show you actually how this will prevent control flow hijacking. So let's say my stack would look like this. I have a bunch of local variables. Let's say even I have my stack canary, and then I have my return address here. Okay, so this stack goes downward. Okay. So as I showed you before, the way that control flow hijacking works is that you kind of like start by writing things. You eventually go down and basically kind of have a pointer that kind of circumvent this and overwrite the return address, and that's how you're gonna actually have a control flow hijacking attack. So basically what you can do is that you can kind of like, by this pointer that's kind of pointing to this return address, if you overwrite this return address to the address of the return-oriented programming pointer, you can like launch an ROP attack, right? But here's what we're gonna do with the shadow stack. So essentially the idea of shadow stack is that we're gonna have a mirror stack called shadow stack, which basically what it does is that for each function, we're We're going to basically store the return address and some other variables if you want to in the shadow stack. Then the way it works is that whenever we call a function, we're going to put things into the shadow stack. But during the execution, we're not going to update the shadow stack. Okay? So if the adversary even managed to overwrite things into the program stack during the execution, since it never has access to the shadow stack, this value, this return address that is stored in the shadow stack, it's not going to be matched with this address, because essentially whenever we have a function call, we're going to store this value into my shadow stack. So I'm going to basically duplicate the value of my return address whenever I'm jumping to a function. So if the adversary even managed to overwrite this, since they never overwrite this, these two values will not match. If these two values won't match, we're never going to return to that address. So we're going to raise an exception, or again, do various different things to enforce this. Okay? If these two values, so in regular system, that overflow doesn't happen, these two values will match, right? So your return address will be the same as the original return address. So you check that, you're good to go, you're going to continue. But if the buffer overflow happens and that address is changed, but the other address hasn't been changed, then you're good to go. You're gonna raise an exception, and then you're gonna be safe against shadow stack. Buffer overflow attacks. Does that make sense? And then of course you might wonder that why the attacker cannot write to the shadow stack, because generally shadow stack is not writable by the program context. Okay, so it's only during the function calls that you kind of store things in the shadow stack. What are the overhead of the shadow stack? Of course, it means that you're copying many things. There are extra steps for every single function call and function returns. That means that the runtime is the performance of the system is impacted negatively, but of course you're going to get security at this system. Okay, and then this is a dynamic defense, right? So it doesn't care about what is your CFG and all the possibilities. It's whenever you call a function, you're going to push things into the shadow stack. So that gives you 100% coverage and 100% security at all times, which is great. There are two ways of creating shadow stacking. For example, people have shown that you can have what we call a direct mapping, essentially saying, okay, for every, let's say, 8 megabytes, I can create another 8 megabytes into the shadow stack. A more interesting approach is the indirect mapping, which essentially you can have a base pointer, which essentially what you do is that you don't need to create two separate memory addresses. What you can do is that for your stack, you can always say that there is a pointer that shows you where that shadow stack is. As long as that information is not available to the attacker, your system will be secure. Okay. So there is various papers talking about this. Usually indirect mapping is a good idea to go with. And people have shown that essentially a good thing about shadow stacking with indirect mapping is that accessing to the shadow stack is essentially as fast as accessing to the regular stack, because all you need to do is another general purpose register that gives you the base. So everything will be offsetted by that. So that's kind of like the idea of a shadow stack. If you're interested, you can definitely take a look more. But it's kind of like the glorified version of the stack canary. This kind of gives you very strong guarantees about buffer overflows. And it's protecting you against backward. It again doesn't protect you against forward. You can, for example, for forward, if you do something like this, will be helpful. But usually you combine this idea with CFI so that you have both forward and backward protections. Okay? Questions? All right. As I said, there is also another option other than CFI, and that's what we call a tag architecture. This is actually getting a lot of traction these days because ARM actually picked this up. So ARM has this, what we call a PAC, or pointer authentication tag system. Essentially, the idea of tag is this, that everything, including data and code, can be tagged whenever we write them to the memory. Okay? whenever we want to read them, we have to use we have to generate the tag in order to be able to read and write to them. Okay, so how does this help? This helps because only the so and then how do we create the tags? The tags can be created by like a Mac. Okay, so it's actually use the keys, the secret crypto keys. Okay, so this way, basically, this means that the adversary cannot generate arbitrary writes because every write has to go through the tag generation and has to be created using the secret key. So for example, if I go through this process of buffer overflow, right? If you remember in buffer overflow, the idea was I want to write here, but I don't just write here. I also start writing the rest of the stack, right? In order to write to these things, each one needs a separate tag, and a separate tag needs to be generated. So here I supposedly create just one write, but in fact I'm making multiple writes. In regular systems, this is allowed because I don't care how many you write, but in a tag system, I cannot do that because every single write has to be done separately using a different tag. Okay, so this basically prevents scenarios where you accidentally write to the memory. Okay, and this is how you protect this. Another nice thing about the tag is that you can also protect not just code but also data. Okay, so you can also protect your data from being accidentally rewritten. Remember, I told you that some of the attacks are data-only attacks that doesn't necessarily change the control flow, but just change the variables. You can protect your variables this way as well, which means that the adversary cannot just write arbitrary values to your tag. Okay, and you can propagate this tag. So there are lots of work shows that you can propagate the tags to the cache and to the memory and to the CPU and all that. And as I said, ARM has implemented this in hardware, so they actually have commercial off-the-shelf processors that supports tag systems called PAC, which you can actually use. Of course, tagging means that every read and write now needs to be checking the tag and recreating the tag, which means that now your read and write to the memory is taking more time. But on the other hand, you're completely removing the issue of any sort of overwrite by the point. So you don't care. You can use any sort of unsafe language. You can do whatever you want. This basically gives you guaranteed cryptography, guaranteed safety of your pointer, which is very, very strong uh, 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 capability, security capability, and of course the cost of losing performance, and also you need to store these tags, so it means that there is also storage overhead. Okay. Next we're gonna actually talk about this. Interesting thing is that people have shown that this can be attacked. There's a very clever way of creating the tags. I'm going to let you guys read the papers. I think one group will present it. And then later I'm going to talk about that a little bit more. Okay? There's also this very interesting paper called Tag Architecture Guide. This is also a very nice Saver survey paper that talk about these tag architectures if you're interested. Any questions? Okay. All right. So that's what we call, that was like things I wanted to talk about prevention. Let's also talk about detection, okay? So prevention, the big problem with prevention is prevention comes with big overheads, okay? Because you need to, for example, check the tags, or you need to check every single, control transfer. You need to have either shadow stack. So these things works really well for high-end systems. But if I'm talking about like a microcontroller, like a very tiny device with very little processor capabilities, very small power consumption, very small memory, then many of these things that I talked about are very hard to achieve, okay? Instead, what we do is that we go from runtime prevention to just runtime monitoring to check the status of the device. So essentially this is what we call remote attestation. Remote attestation is this process where you want to check the status of a device. Let's say, for example, you have a sensor, a camera installed in your home. You want to see occasionally whether or not this camera has been hacked or not, whether it has been code has been changed in the device or not. So what do? You want to see whether there has been any change in the content of the memory of that device. So you know, for example, that okay, this camera has this particular firmware, okay? And you know that the content of the firmware is like a very particular code. You know exactly every single instruction within that code, okay? So you know that if this system is correct, there has to be this firmware and nothing else in the system, okay? So if the adversary somehow managed to install and inject code, what will happen is that the content of the memory in that device will be different, right? So essentially somewhere in this memory, if this is the memory of the device, somewhere either new things has been added or few things that was there has been modified, right? So here's what I'm going to do. The idea of remote attestation is that I'm going to compute a response, usually a hash, over the content of the memory. And I'm going to send this hash. So basically, I'm going to hash this entire thing. And I'm going to send this hash to whoever wants to see the status of my device, okay? What they can do is that since they know the ground truth, they can also hash the ground truths themselves. What they're going to do now is that they're going to compare these two hashes. If they see that these two hashes matches, it means that this device hasn't been modified, okay? If these two hashes are no longer matches, means that something into that memory has been changed, okay? Again, we're not preventing that memory to be not hacked. So if I see that these two doesn't match, it means that this device is gone. This device has been compromised. At least I know that I can no longer trust that. So either I can go intervene and maybe take it out and reset it. Maybe I can push an update. There are various things I can do with that device, but at that point, at least I know that this device is no longer trusted. Yes.
Device itself, like memory itself, or like how does this work if the device just like normally uses its memory and modifies it itself?
So the idea is that if you want to modify your own memory, you have to go through what we call a secure update. Okay. So the idea is that you can change. So for example, every system has typically a program memory and a data memory. Okay. It could be part of the same address space, or it could be separate. When I'm saying memory here, I mean program memory. Okay. So the idea is that I check the data. I don't care. You can just write whatever you want to it. I'll just check the program. I want to make sure that the code that you're executing in this system has not been modified. But of course, let's say, for example, today you decide to update the firmware. What will happen is that this process goes through a secure update. So for example, you issue an update, you update this firmware, this will be hash prime, this will also be hash prime, and things will be again safe. But you're on the right track of thinking about how can this be done. And as I said, this could be a rare event. You can also check it every hour, depending on what you want. Of course, at the most extreme case, this could be a runtime thing, right? So you can continuously check this, which is essentially you're reverted back to those runtime prevention scenarios. Remember here, I want to reduce the overhead by not running this all the time, okay? So as I said, this is the protocol of remote attestation. Remote attestation is what we call a challenge response paradigm. If you remember, we talked about challenge response paradigm in the past as well when we were talking about distance bounding, and said that in distance bounding we also had a prover and a verifier. Here we also have similar two-player game. The prover is the device in question. So this would be, for example, your camera. The verifier is some trusted device that has access to the ground truth. The prover is the one that does the measurements. As I said, for example, the measurements usually is computing some hash function over the content. It sends it to the verifier. The verifier will use it to check whether or not this prover can be trusted or not. If attestation is passed, it means that I can trust the prover. Otherwise, prover is compromised. I can do other things in order to make sure that it works. Okay. And this is what I said. So essentially, the goal of the remote attestation is that the prover needs to show that their memory has not been modified. Okay. How do they do that? They compute a hash over this content, send the result back to the verifier. The verifier knows the correct answer, checks the correct answer with this. If they two match, it means that the system is secure. So the big thing about attestation is that this system has to work even if the adversary has the full control over the device, right? So essentially, we need to create a mechanism where, assuming that the device has been fully compromised, they cannot lie about their status, okay? So the idea here is that I want to be able to detect whether or not this device is compromised. If the attacker controls this and somehow lie to us about the status, this this attestation protocol fails. Okay, I want to have some guarantee that if this device has been modified, I can for sure detect that this device has been modified. So that's the security aspects of remote attestation. So question for you guys: what can the adversary do? So let's say I have this method that I send you a request of compute your hash and send your hash back to me. And now you are an adversary. You want to lie in this game. What can you do? Yeah.
Take over, you compute the hash,
Mm-hmm.
and then you remember the hash, and you replace your own firmware,
Mm-hmm.
and then you just, whatever they ask you, you just return the old hash.
Yes. Okay. It's great. It's one thing you can do. That's a very common way. Anything else?
You could copy the firmware stuff into a different place in memory, and then whenever the hash is requested, you can.
Yes. Yes, you can always at least the lines that you change, you can also save it somewhere, and then whenever it comes, you can always forward it to those. That's exactly. These are the two very good answers. And so now, do you have solutions for those? Do you know how we can fix this problem? Yeah.
Kind of like challenge with a nonce.
Mm-hmm.
And change it so that they can't just remember. We need to like hash it together with some new value.
Yes. So you hash it with, but what the nonce fix that problem? So if I save it somewhere else, I take the nonce and use that saving and then recompute it, right? So how can we fix that problem? So the idea, so let me show you what is the, so there are two problems, right? The first problem is that I can have a replay attack. Essentially, the idea is that before I change the content of the memory, I compute the hash, I save this hash somewhere. Whenever someone asks that give me the status, I will just send this, right? So how can I fix this? There's an easy solution. I can basically say that I don't send just a request. I send the request with nonce, such that the hash should be content of the memory plus the nonce. So should be mem and nonce together, which means that I cannot just pre-compute this. Every time I have to compute it. But then the more sophisticated attack in this system would be that if I'm changing this memory, here's what I'm going to do. Let's say I have some spare, memory or some additional space in the memory. What I'm going to do is I'm going to copy this here. Then I'm going to change this, right? And then and then of course, when I'm going to hash, whenever a request comes, instead of computing the hash over here, I'm going to compute the hash over here, and then I'm going to send this. I'm going to run things from here, but whenever someone asks me, I'm going to give you this, right? So I have kind of a dual identity. So how do I fix this second problem? Yeah.
Sort of so there's got to be some way of figuring out that like this software is using too much memory or too much storage or something like that.
Well, the adversary, yeah, could be. but the idea is that the adversary has full control over the system. So the adversary has the entire memory at their disposal. But yeah, so one way actually to kind of like to help you with the answering is if somehow we reduce this such that there is no spare memory, then the adversary cannot use this trick. So that's one way of fixing this problem, right? Anything else you want to say something? Oh, you was going to say that? So do you have an attack? So let's say we eliminate all the possible space for the attacker. Can you think about a clever way of still doing this? Yeah. You compress it, right? So if you can compress the memory, then although you think that there is no space, but there are space. So actually there are attacks that shows that compressing can work. Yeah.
Maybe you have like a piece of hardware
Mm-hmm.
that you talk to, and the hardware computes the hash of the firmware, and the firmware doesn't get to compute its own hash.
Mm-hmm.
But this piece of hardware just takes all the memory, computes the hash, and returns it to you instead.
Okay, that's a great idea. So that goes to what we call a root of trust. So essentially, you need something into the system that you trust. Instead of asking the kind of the untrusted that you prove your trust, you ask the root of trust that you go and check the guy, see what they're doing, kind of thing, right? So yes, you can have a root of trust that do this computation, and that's exactly what we're going to do as part of this. But let's say I don't have a root of trust. Can I do something else? So this is what we call as hardware solutions or hybrid solutions, which we're going to talk about. But let's see, I don't have anything that I can trust. Can I do something to fix this problem?
So in this case, we're like assuming that we compress the memory and then now have memory in order to like rewrite stuff, right? So if we, for every possible instruction that an attacker could do, we could do some sort of, we make sure that the only instructions they can do on this particular architecture is safe memory instructions,
Mm-hmm.
then they wouldn't be able to overwrite like that.
Mm-hmm. But you want the system to also operate normally. So you cannot have only memory instructions, right? So you want to have add instructions, you want to have multiply instructions. So this is like a regular system. So it has a regular code and
Instructions like very memory safe. You make them all.
well, the idea here is that you somehow can like, so this has to be also, so the thread model here is that it's not just, let's say, buffer overflow. There's someone can actually physically, let's say, connect to the device and reprogram the whole firmware, right? So it's not just buffer overflow that we are worried about here. We are worried about all the three conditions, like someone download the malware, someone just rewrite the whole memory, right? Because, for example, this is your security camera. The adversary can just literally go and like plug it in and write things. You want to check the status of your security camera. Yeah. You hash all of the memory, okay? Okay. But yes, that's a good idea. But what if when I'm hashing, since I am the adversary, I never actually, so I kind of like move this as I'm hashing. So let's say this is my entire memory. This is the part that is kind of questionable. This is a good part. When I'm doing the hashing, I first move this here and then like fill it with zeros or some old values that I have. And then when I'm hashing this here, I move this back up, then the hash is never sees that particular code, right? Because I can copy things before hashing and copy it back after hashing as an adversary, right? So there are like these dynamic ways of doing this as well. But you're getting close. And by the way, this is your like CA number 3. We ask you to do this kind of various different types of remote attestations. And this is like a very established area of research, lots of attacks. So all of these things is actually like 20 years of research. So like the very first one was what we said, and like this compression, for example, was a paper that someone published and show that compression was an attack. But it's interesting that we're getting close. But there is something fundamental that I can use in the system to protect it. Yeah.
I mean, is there a way that we can calculate the time
how much it takes to hash.
Exactly. That's one thing that we can do, right? So all of these things will require time, right? So if the adversary needs to compress and uncompress, or if the adversary needs to move things around, all of this is extra computation, okay? So if I can use not only just the hash, but how long does it take for the adversary to hash things, then I can probably fix some of these issues. There might be some more clever attacks that we're going to talk about, but this is one actually very sophisticated, like a very common way of protecting the system. Can you also think about an attack for that? Yeah.
Figure out a faster way to do the hash.
Yes, you figure out a faster way to do a hash. Actually, that's usually harder to do because hash functions are so actually hash functions are designed to be secure.
You figure out you figure out how to do some other code faster.
Yeah, so either like you find, let's say, a faster compression code, you either figure out how to make your processor faster, or there is one thing called proxy attack, which you offload this to some other friends that you have that has a better processor. So the hash computation comes, you don't compute the hash, you send it to someone else that has faster processor. And they can, this process of sending, receiving, and then sending it back is then cannot be done. Anyone else wants to like bring final comments? I'm not gonna give you answers. The answers will come in the next lecture. But we are kind of like, using timing, using the various different things can help this process. Anyone wants to suggest any other solutions? Yeah.
More of a question, but we're using time to hash, and we had to give that time to hash information back
Mhm.
to the verifier.
Mhm.
So there must be something special about that time to hash information. Like, are we like hashing that as well? Like, how are we proving that?
Well, the receiver can time it, right? So here's how it works, right? So since this is a two-player game, the verifier will start a timer at this, like T1, send the request, and then whenever it receives is T2. So I measure that, right? So I can do that. Okay, so talk to you guys next time. I'm gonna give you some answers for this.